In this video for exercise 1324, we're going to follow that same path of reasoning that we've built up in the last couple of videos in order to do some multi-step synthesis exercises. Now, here, the first thing we always want to ask ourselves is, do you form a new carbon-to-carbon bond? And if you do, then for this chapter so far, you'll know you'll need to use a Grignard reagent. That's the only new carbon-to-carbon bond-forming reaction we've learned this semester. We'll add to that as time goes by. But you'll notice that on this molecule on the left, you have a 5-membered ring, and then you have 2 carbons attached to it. And in the molecule on the right, you have a 5-membered ring and 2 carbons attached to it. So you have the same number of carbons on both sides. That means you aren't forming any new carbon-to-carbon bonds. You'll know you'll form a new carbon-to-carbon bond because you'll have more carbons in your molecule. So we don't have more carbons, we know we don't have to do that. So really, we're just focusing on functional groups changing or interconverting. And that's what this table that we built in that previous video describes. Now what they're giving us here is an alkyne, so we're starting with that triple bond. And what we want to get to is an alcohol. So we want to end up over here. Now there are many ways to do that, right? We could turn the alkyne into an aldehyde or a ketone, and then we could reduce it. That's one possible synthesis. Or we could turn the alkyne into an alkene, and then do an addition reaction. That's another possible synthesis. So there are many ways of tackling this and solving this problem. Let's sort of do 2 for this first one, just to show that. And then for the future ones, I'm just going to show how you could reason through this for one example. And if you have an example that I'm not showing and you want to know if it's valid, definitely come visit me in my office hours. I would love to go over any possible syntheses that you have. Okay, so we have an alkyne. Now, we know that we want an oxygen. When you compare this molecule, the starting material, to the end product, one thing you'll notice is that you have no oxygen at the beginning, and you do have an oxygen at the end. So how do you add an oxygen onto here? But by even asking that question, you give the answer away. You need to do an addition reaction. Excuse me. Now, we've seen additions before. We used some additions in the previous video. If you do an addition on an alkyne, though, in the previous video we did them on an alkene. If you do an addition on an alkyne, then you end up getting keto-enol tautomerism. Now I have a video that reviews that from Organic Chemistry 1 in the Organic Chemistry 1 review playlist. So if that sounds unfamiliar to you, I strongly recommend you watch that video on keto-enol tautomerism. So let's say you wanted to do the addition. So you take that same molecule, and what you want is you want to add an oxygen on this end carbon there, this end carbon right here. So here that's where you want to add it. Now, if you compare those 2 carbons in the triple bond, the one on the end is only bonded to one other carbon, so it is primary. The other carbon is bonded to 1, 2, so it is secondary. We want the oxygen to go on the less substituted carbon. That means the hydrogen would go on the more substituted carbon, and that would be anti-Markovnikov. So we want anti-Markovnikov addition of an OH. And that it is done by hydroboration oxidation, as we've seen before. So you use 9-ppn, first step, second step, sodium hydroxide, and hydrogen peroxide. Now what that does at first is it takes your triple bond, it takes those electrons and it moves them. And here I'm going to just make this trigonal planar, right? Because when you have a triple bond, it's linear, but when you have a double bond, it's trigonal planar. So I'm just going to put that zigzag in there. But what you'll get is this will add the oxygen onto the less substituted carbon. So you'll have an oxygen here, an OH. Just like before, just like with the alkenes. right? If you look back at the previous video, we used hydroboration oxidation in this example, right? It put the OH on the less substituted carbon. If you look back at your work for B in the previous exercise. And so likewise here, it puts the OH on the less substituted carbon in the pi bonds. And this is called an enol. You have an alkene, so ene. You have an alcohol, so ol. So this is an enol. And the enol interconverts to either an aldehyde or a ketone. It's called keto-enol tautomerization. And tautomerization is where a hydrogen moves in order to make room for the movement of electrons. So tautomers are two molecules that are exactly the same except for the placement of hydrogen and some electrons. So the enol becomes, and notice this is an aldehyde. So the enol becomes an aldehyde through that tautomerization. And so that's what you get if you try to add an OH onto this alkyne. And so if you look back at this chart that we had, that would be like using this reaction to get your aldehyde. And you can see where we would need to go from here. If you had this chart in your mind, you would have to use a reducing agent. But let's say you forget the chart or something. All you have are your analytical abilities. How can you look at this and deduce you would need to do a reducing agent? Use a reducing agent. So we need to get from this final product, what we have now, to this final product. There's the 5-membered ring with the 2 carbons, 5-membered ring with the 2 carbons. We have an oxygen, and there's an oxygen. So all of the atoms that we need are the same. The difference is the number of bonds to things. In the starting material, we have 2 bonds to an electronegative element, and where we end up, we only have 1. The number of bonds to an electronegative element decrease or reduce. That type of bond, that type of change is called a reduction. So we have a reduction here. Now, you would want to then ask yourself, do we need to use a weak reducing agent like sodium borohydride, or should we use a strong reducing agent like lithium aluminum hydride? And in this particular case, either would work. Remember that sodium borohydride reduces aldehydes or ketones, but not carboxylic acids and esters. And lithium aluminum hydride reduces everything. So if you needed to, you could always use lithium aluminum hydride. The one exception is if there are also carboxylic or acids or esters that you do not want to change. In that case, you would use sodium borohydride. So you can reduce aldehydes or ketones without changing carboxylic acids or esters. So here you use lithium aluminum hydride. Well, let's use that just for argument's sake. And remember, whenever you use this, if you think back to the mechanism, it's a 2-step process. The first step is the hydrogen nucleophile attacking the carbonyl carbon. And then when that happens, the pi bond moves on to the oxygen, gives the oxygen a negative charge, so you have to do a proton transfer from water to stabilize that. So don't forget that second step, that water there. And so that is one possible solution to this exercise. Now another thing we could have done, we could have taken the same thing, analyzed it in a slightly different way, and come to a slightly different conclusion. So this answer that we just had, that would be like taking this path to our product, but you could take another path. You could, for example, go from the alkyne down over to the alkene, right? You could use hydrogen gas and Lidlar's catalyst, or you could use dissolving metal reduction. And then you could use one of those addition reactions that we discussed in the previous videos to get the alcohol. So that would be another way you could do that. Or, if you really wanted to, you could get to the alkene, then you could do hydrohalogenation, and then you could get to the alcohol. So there are many, many ways that you can get from this one reagent to the other. Like I said, in these videos, I just want to reason through one example to help sharpen your skills, your analytical skills, with these types of problems. But so long as your exercise or so long as your synthesis will create the necessary transformation, I'll give you complete credit. Okay, let's try B. So first question, do you form a new carbon-to-carbon bond? In the molecule on the left, we have 3 carbons. The molecule on the right, we have 3 carbons. And so the number of carbons doesn't change. Therefore, we do not need to use a Grignard reagent to form a new carbon-to-carbon bond. So we're just looking at functional group interconversion, and that's going to be that table that we built in that previous video. So here, we're going to start with an alcohol. We'll start with an alcohol, and we'll end up with an alkyne. So it's sort of the reverse of what we did in the last video. Now in this one, you might think, okay, well maybe first I can oxidize it, but there's no way to get from that aldehyde or ketone to the alkyne. So that way isn't available to you. Another option is we could turn the alcohol into an alkene, and then we can turn the alkene into the alkyne. Okay, so let's try to reason through that. We see an OH here, we don't see the OH there. That means it disappears. How do you get rid of that OH? You eliminate it. And so the type of reaction you'd want to do is an elimination reaction. Now there are 2 types of those. There's E1 and there's E2. You would know to do E1 if you have if the alcohol is a primary alcohol. You would do an E2 if it's, I'm sorry, got that backwards. You'd know to do E1 if you had a tertiary alcohol, and E2 if you had a primary. For secondary, you could technically do either, but usually E2 will be more efficient. So here, the OH is bonded to a carbon that's bonded to one other carbon. So that's a primary alcohol. And so what we're going to do is an E2 elimination. Now, remember that when you do these eliminations, that you always end up forming a pi bond between the alpha carbon, that's the carbon that has the leaving group on it, and the beta carbon. Now we only have one beta carbon, so we don't have to worry about the Hoffman or Zaitsev product here, because there's only one place where that pi bond could form. However, when you do an E2 reaction, the first thing you have to do is turn the OH into a good leaving group, because right now the OH is a bad leaving group. So in your first step, you would want to use tosyl chloride and pyridine. And we've walked through the mechanism for that in a previous video in this chapter, what tosyl chloride looks like and how it works. What you end up getting after you use tosyl chloride is this, it's called a tosylate. And so this is now a good leaving group. And now you can do an elimination. It doesn't matter what type of base you use. I myself, if it doesn't matter, like this, especially if it's a primary, if the leaving group is on a primary carbon, I like to use a bulky leaving group because that kind of prevents substitution side reactions. Right? If you have a skinny one, then the base could also potentially function as a nucleophile, and you could get a substitution reaction. So I like to use TBUOK if it doesn't matter, and you want to get the elimination reaction. So potassium terbutoxide, that would do the elimination reaction. What you'd end up with there is you would end up kicking this leaving group off and forming the pi bond. Okay, so now, and so if you compare this, we've sort of used these, we've done this step, and now we are at this alkene. So now we just need to go from the alkene to the alkyne. To form pi bonds, you always do elimination reactions. Right? You can tell even just from what we just talked about, we did an elimination reaction, we formed a pi bond. So anytime you form a pi bond, you have to do an elimination. Now what we have is one pi bond, what we want is 2 pi bonds, so we need to do an elimination. But this doesn't have anything to eliminate. So we have to add leaving groups. And the classic leaving groups are halogens. Now if we add something on here, we're going to get rid of a pi bond. Right? So we're only going to have single bonds. And if we only have single bonds, then that means we're going to have to do 2 eliminations. each elimination will form a pi bond. So we have no pi bonds, 2 pi bonds, we have to do 2 eliminations. So we have to really add 2 leaving groups. And that's why you would add Br2. If you add Br2, one bromine goes onto one of the carbons in the double bond, the other bromine goes onto the other one in the double bond, and now you're ready to do the elimination. Now, if you're trying to get 2 elimination reactions done at the same time, you want to use a strong base, and you'd want to use excess of it. Now, the letters XS are standing as abbreviations for the English word excess, so it's not anything special. It literally is what it sounds like, excess. And the strong base that you have learned about to do this from Organic Chemistry 1 was sodium amide, so NaNH2. And what that does is it'll take these 2 leaving groups, it'll do 2 elimination reactions with them, and you'll end up getting your alkyne. Now, if you're ever interested in seeing the mechanisms for this stuff, because the mechanisms are really important, reach out to me. They are available to you on our Blackboard page. I have or on our page online, our courses page online. I have links to the videos I made for Organic Chemistry 1, and in those videos I go through the mechanisms for all of these reactions multiple times. And if you ever have trouble finding them, don't feel funny reaching out to me. I would love to direct them to you. I'm so excited if you ever want to learn something. Anytime you want to learn, let me know and I will help you. That is a beautiful thing that I really treasure. So that'll do that elimination twice. And you might at first think there's that hydrogen there, but remember you have excess strong base, and bases rip hydrogens off. And in Organic Chemistry 1, you talked about how those hydrogens on terminal alkynes are acidic because the sp hybridized carbon there pulls the electrons in the negatively charged lone pair towards the nucleus better than sp3 or sp2 hybridized, and so sp hybridized carbons are fairly acidic. And so if you have this acidic hydrogen and this very strong base, you could rip the hydrogen off, and the electrons in that bond become a lone pair with a negative charge. And that's why to get the final stable product, which has a hydrogen there, you have to do a proton transfer and shake that up with some water. So this excess base does do both of the elimination reactions, but it also rips the terminal hydrogen off, the hydrogen on the end of the chain off. And so to put it back on, you shake it up with some water. And so everything in this green area, would be what you would want to write for full credit in your answer. If all you wrote were the reagents, you would not get full credit for this question, even if they were the correct reagents. It's important to me that you know, that I can see that you know how each reagent changes the molecule. So make sure you draw each of those intermediates there. Okay, so that's B. Let's try C. So in this one, we're going to follow that same procedure. Do we form a new carbon-to-carbon bond? Let's see. In the reactant, we have 4 carbons. In the product, we have 4 carbons. So we have the same number of carbons. That means we don't need to add one, so we don't need to form a new carbon-to-carbon bond. So we don't need to use a Grignard reagent here. So all we have to do here are functional group interconversions. That's using this table that we've built up in that previous video. So here we're going to start with an alkene, and we want to end up with an aldehyde. So we're starting with an alkene. We want to end up with an aldehyde. And there are many ways you can do this. You can turn the alkene into an alkyne, and then you can do a hydration. Or you can do a hydration and then do an oxidation. And so there are several answers you can get for this. I'm going to do the hydration and the oxidation because that involves reactions that we learned in this chapter, the oxidation in particular. But we also discussed hydration a little bit at the beginning. So that's what I'm going to focus on here. So you look at the starting material, there's no oxygen. You look at the product, there is an oxygen. So what do you have to do? You need to add an oxygen. You're going to do an addition reaction. To add an oxygen, you're either going to do acid-catalyzed hydration, oxymercuration demercuration, or hydroboration oxidation. That will depend on where you want the oxygen to go. Now on these 4 carbons, if we number them from right to left, we want the oxygen to go on carbon number 1. So if we think about this molecule, we want the oxygen to go on carbon number 1. So that's where we would have the alcohol. Okay, well, how do we make sure the oxygen gets there? For that, you need to know whether this is Markovnikov or anti-Markovnikov addition. Look at the original alkene. The carbon at the right in the double bond is only bonded to one other carbon, so that's primary. The carbon in the middle is bonded to 2 other carbons, so that is secondary. We want the oxygen to go on the less substituted carbon. The hydrogen would go on the more substituted carbon. If the hydrogen goes on the more substituted carbon, that is anti-Markovnikov addition. And the only anti-Markovnikov addition of an H and an OH that we know is hydroboration oxidation. So that's 2 steps. The first step is 9-BBN. The second step is hydrogen peroxide, H2O2, and sodium hydroxide. And so here we're taking this purple route. Notice you could not use any of these. The only one you can use is the third one, hydroboration oxidation, because that's the only one that is anti-Markovnikov. So remember that you need to know these reagents by heart, but you also need to know the details about them. Markovnikov, anti-Markovnikov, Zaitsev, Hoffman, etc. Okay, well now we have this OH, and what we really want to do is we want to oxidize it to our aldehyde or ketone. So if you compare what we have now with what we want, we have the same number of carbons, we have the same number of oxygens, the only difference is the number of bonds to the oxygen. So in this first molecule, we have 1 bond to the oxygen. In the last molecule, we have 2. The number of bonds to an electronegative element increased, and so you would see that and you'd say, oh, not a problem, that's an oxidation. Okay, now what do we use? There are 2 possibilities to do an oxidation. We could use PCC in methylene chloride, or we could use sodium dichromate in water and sulfuric acid. Which one of those is the one we want to use here? To answer that, we have to look at what type of an alcohol we have. Look at the carbon that has the OH on it. How many other carbons is that bonded to? Just 1. That's a primary alcohol. What we want is an aldehyde, right? This is a carbonyl with a hydrogen bonded to it, so it's an aldehyde. So how do you turn a primary alcohol into an aldehyde? The only way you can do that is with a weak oxidizing agent. So you'd have PCC, pyridinium chlorochromate, in methylene chloride. If you used the strong oxidizing agent, if you used sodium dichromate, let's say you did that, what you'd end up with is the carboxylic acid. This is a strong oxidizing agent. So you don't want that, you want the aldehyde, so you have to make sure you use the weak oxidizing agent, PCC, pyridinium chlorochromate. Okay, and that's it. That would be the synthesis for that one. So everything in this box, that's what you would want to include in your answer on an exam. All right, let's try D. So for D, we're going to always ask ourselves that first question: do we need to form a new carbon-to-carbon bond? Do we need to use a Grignard reagent? Now here, our original carbon chain has 4 carbons. Our product has 4 carbons. If you have the same number of carbons, you don't need to add one. You don't need to form a new carbon-to-carbon bond. So we're not going to use a Grignard reagent here. Next, functional group interconversions. So that's using this table that we've built up in that previous video. So here, what we start with is an alcohol. What we end up with is an alkane. So we start with an alcohol. What we end up with is an alkane. So how do you get from an alcohol to an alkane? Well, there are several ways. You could do an elimination, and then you could do hydrogenation. So that's one possible way. If you really wanted to, you could turn the alcohol into an alkyl halide, do that elimination, and then do the hydrogenation. And there are other ways too. The shortest one is that first one that we talked about. So let's sort of analyze that and just show how through reasoning you could come up with that sort of synthesis. So we look at these two molecules. We notice we have an oxygen in the starting material. We don't have an oxygen in the final one. So what do? You have to get rid of that oxygen. Get rid. The technical term for that is eliminate. We need to eliminate that oxygen. So we're going to do an elimination reaction. Now there are two types. There's E1 and there's E2. So for this one, E1 you'd do if you had a tertiary alcohol. E2 is if you'd have a primary alcohol. Here we have a secondary, right? If you look at the carbon that has the OH on it, that carbon is bonded to two other carbons. So it is secondary. So really you could do either an E1 or an E2. Now notice, in this case, the OH, that's the alpha carbon. Every carbon that the carbon that has the OH on it is the alpha carbon. Every carbon that the alpha carbon is bonded to is a beta carbon. We have one to the right and one to the left. We have two beta carbons. So if we do an elimination reaction, we could get the pi bond forming in two directions. We could either get an elimination reaction where the pi bond forms to the left, so you eliminate that and the pi bond forms to the left, or we could do an elimination reaction where the pi bond forms in the other way, to the right. So either one of those. Now, in this particular case, it doesn't matter. Wherever we put the pi bond, all we're going to do is hydrogenate it to get rid of it, so it doesn't matter where it goes. In general, though, if you have a functional group, you always want the pi bond to form toward the functional group. You want it to go in the direction of the functional group. So for example, if I had an OH here on the right side, then I'd want to form the pi bond toward the right side. Because really, when you see these functional groups, what you want to see, or you do want to see the specific functional group, but you also just want to see a changeable place on the molecule. What you'll find by the end of the semester is that every functional group could be changed to any other functional group. So when you see a functional group, what you want to see is a changeable part, a part you can mold and shape, like clay. So if you see the alcohol here, you want the changeable part to be on the right side. That's why you have the alkene on the right side. Whereas if you had the OH to the left, then you'd want to form the pi bond to the left. So that's one of the ways you can think about. One of the ways you can think about whether you want to you can think about which direction you'd want to form the pi bond in. Just for practice, though, while we have this up, even though it doesn't matter which alkene we get, let's just classify each of these alkenes just as a sort of quick review. If you look at the two carbons in the double bond, and you think about how many carbon chains are coming off of the double bond, in this alkene on the left, we have 1, 2. That makes that alkene di-substituted. If you look at the two carbons in the pi bond on the right, think about how many carbon chains are coming off of those. There's really only one. That makes that mono-substituted. So mono is less than di. Whichever product is less substituted is called the Hofmann product. And whichever product is more substituted is called the Zaitsev product. So this is a review from Organic Chemistry 1. To get the Hofmann product, you use a bulky base, like potassium tert-butoxide. And to get the Zaitsev product, you'd use a skinny base, like sodium hydroxide, sodium methoxide, sodium ethoxide. The ET here stands for an ethyl group, right? So 2 carbons. Okay, now there's reasoning behind that, and I have that reasoning in the videos that I have for the review for Organic Chemistry 1. This is a little far afield to dive into that here right now. But I did want to just give you that practical tip, that practical review about the difference between the skinny and the bulky bases and the Zaitsev and the Hoffman product. One thing to note is no matter what you use, you will always get both of these, technically. You'll always get a mixture. It's just a matter of which one gives you the major product. The bulky base will give you the Hoffman product as the major product, and the skinny base will give you the Zaitsev product as the major product. So either of those would be fine. Once you have those, if you wanted to turn them into your final product, excuse me, all you have to think about is, well, I have a double bond here, a pi bond. I don't have a pi bond there. If a pi bond ever goes away, that means you did an addition reaction. Addition reactions use the extramolecular glue that a pi bond is. Because remember, electrons are the glue that keep atoms together. If you have a lot of electrons in a small space, like you do when you have a pi bond, then you have extramolecular glue there. You can use that to add new things onto the molecule. In the process, the pi bond will go away. It'll be used to stick the new things onto the molecule. So if you ever see a pi bond go away, you know to do an addition reaction. But what did we add? I don't see anything here. There's no OH, there's no halogen. Whatever's there, there must be something there. Whatever's there is invisible. And the only element that's not drawn in, the only element that can be implied and be invisible, is hydrogen. And if you draw the hydrogens in, you could see this more clearly. So notice that this molecule here has only one hydrogen there, only two hydrogens on the carbon at the end. This has two hydrogens there and three hydrogens at the end. So we've added hydrogens. We've added two of them, one on each of the carbons. So you do a hydrogenation. So H2 gas, you'd bubble that through, and you can use either platinum, palladium, or nickel as your catalyst. I'm just going to use platinum. So you could use either of these. I know I have this drawing here from the Hoffman product, but either of those would work. And so you wouldn't have to draw both, just one of them. And so this type of stuff in here, that's what you'd want to include for your answer. And you'll notice that's what we highlighted here, right? We started with the alcohol, we did the elimination, and then we did the hydrogenation. And that's D. Okay, E. And I think, okay, E, and then we have F, E and F, and then that's it for this exercise. So first E. Okay, first question, do you form a new carbon-to-carbon bond? Let's look at the number of carbons. We have 1, 2, 3, 4 in the reactants. In the products, 1, 2, 3, 4. So the number of carbons doesn't change. That means you don't make a new carbon-to-carbon bond. If you make a new carbon-to-carbon bond, the number of carbons would change. So it doesn't, so we don't do that. We're not going to use a Grignard reagent in this exercise. So all we need to do is look at how the functional groups will need to interconvert or change, and for that, we'll use this table that we drew out in that previous video. Okay. So, when I look at this, what I see is I have an oxygen here. Oh, and actually first, so if we're doing the functional group interconversion now, first let's see what functional groups we have. They give us the aldehyde, and then they give us an alkene. So that's what we need to move between. We're starting with an aldehyde, and we need to get to an alkene. So how can you do that? Well, as usual, there are several ways. But one way is you can do a reduction to get to an alcohol, and then you can do an elimination. Okay. And so here, let's say you forget that table, you want to sort of reason through this. How could you do that? Well, you notice you have an oxygen here in your reactant, and you don't have that in your product. So you need to get rid of the oxygen. You need to eliminate it. So we're going to have to do some sort of an elimination reaction. Now, there's no way to kick a double-bonded oxygen off of a carbon chain in one fell swoop. It's really stuck there. That's what these two bonds are saying. That oxygen is really sticking to that carbon chain. So there's no way to get rid of that in one step. But we can get rid of it one bond at a time. First, we can break one of the bonds to the oxygen, and then we can break the second one. and that will allow us to eliminate the oxygen altogether. So if we eliminate one of those bonds, we would be turning this into an alcohol, right? What that second bond does, that'll be a bond. Those electrons will now go to a hydrogen. So we're giving the oxygen something else to bond to so that it doesn't bond to our carbon chain, which we know we don't want it on. Okay, well, who knows what we'll do with this, but we know we're going in the right direction when we do that because the oxygen is being held less tightly on the molecule. So what type of a transformation is this? Well, we start out with the carbon with 2 bonds to an electronegative element. We end up with just 1. The number of bonds to an electronegative element decreases. That's reduction. Now, there are 2 types of reducing agents. There's sodium borohydride. That's the weak reducing agent. Or there's lithium aluminum hydride. That's the strong reducing agent. Lithium aluminum hydride will reduce aldehydes, ketones, carboxylic acids, and esters. Sodium borohydride will just reduce aldehydes or ketones. Now here we have an aldehyde, carbon double bonded to oxygen with a hydrogen on one side. So either would work. But just in terms of simplifying your life, I might use lithium aluminum hydride all the time, except when you have both an aldehyde or ketone and a carboxylic acid on a molecule, and you only want to reduce the aldehyde or ketone. That's the case where you use sodium borohydride. Otherwise, lithium aluminum hydride would work. Now, the practical risk of lithium aluminum hydride is that it's a very strong reagent. So if you have a big molecule, like right now we're dealing with small molecules, but let's say you're a pharmaceutical chemist, you have this precious molecule people have spent months working on, it's huge, gigantic. If you use lithium aluminum hydride, this strong reagent, it could destroy some of your molecule. So that's the only disadvantage to these strong reagents. Weak ones will be more sensitive, and it's less. Lithium aluminum hydride is a little bit like a chainsaw, or like a bag of piranhas. So it can sometimes damage your molecule. So that's the only liability with strong reagents. But in this class, we don't have to worry about that so much. We're just trying to come up with a sketch, a rough draft for how you could accomplish transformations. And lithium aluminum hydride would do this. Now remember, when you use lithium aluminum hydride, you use it in 2 steps. You use the lithium aluminum hydride, and afterwards you have to do a water wash. Now you're going to have to draw the mechanism for this reduction like this on the test, either with sodium borohydride or lithium aluminum hydride. So be sure, so hopefully this makes sense to you from the mechanism that you've mastered. Notice that if you use sodium borohydride, this particular book likes to use methanol as the solvent, so that's CH3OH. This Me is just the CH3. And this is serving the same purpose as the water here. It's just a proton source, so you could do a proton transfer. Notice also with sodium borohydride, when you use that, it's not in separate steps. This is all together. With lithium aluminum hydride, these are in separate steps. Okay. So now we have this alcohol. And so we're closer to getting our alkene. We just need to eliminate it. I'm going to erase this hydrogen here. It is still there. It's just implied. So we have to eliminate this alcohol. And so elimination reactions have 2 types, E1, E2. Here, to decide between them, you'd look at the carbon that the alcohol is on. You know you do an E1 reaction if you had a tertiary alcohol, and an E2 reaction if you had a primary alcohol. Look at the carbon that the OH is on here. It's only bonded to one other carbon, so that is a primary alcohol. So we're going to do an E2 reaction. An E2 reaction requires 2 steps. The first step is to turn the OH into a good leaving group. Oops. First step is to turn the OH into a good leaving group. And so we'd use tosyl chloride and pyridine. After you do that, that will turn into a tosylate. So instead of the H, you'll have that tosyl group. And we drew the structure for that in a previous video. And once you have that awesome leaving group, all you have to do is add your base. Now, here is where you'd have to decide whether you'd use a skinny base to get your Zaitsev product as a major product, or a bulky base to get the Hoffman product as the major product. In this case, it doesn't really matter which one you use, because the alpha carbon, that's the carbon with the leaving group on it, only has one beta carbon attached. So there's only one place where you can form the pi bond. Whenever there's just one place, whenever you have a primary, the leaving group on a primary carbon, I like to use potassium tert butoxide, the bulky base, because that discourages any substitution side reactions. The tail of this is so bulky, even though the negative oxygen would function as a nucleophile, the tail kind of prevents it from getting close to the carbon chain. And so you get a more efficient elimination reaction with that. And there it is. That would be a possible synthesis. This whole thing in that box would be your solution that you would want, how you would want to write your solution on a test. You don't just want to write the reagents. That would sort of be half credit. The other half is showing me that you know what those reagents do. All right, and that's what we saw here in this thing. We did a reduction to get the alcohol, and then we did an elimination to get the alkene. All right, last one for this exercise, F. So the first thing we want to ask, as usual, is do we need to form a new carbon-to-carbon bond? Well, let's look at the number of carbons. We have this sort of 4-carbon chain with a methyl group, 4-carbon chain with a methyl group. If you have the same number of carbons, then you did not add any carbons, you did not form any new carbon-to-carbon bonds, and so you don't need to use a Grignard reagent. So all you have to worry about are the functional group interconversions, and those are the ones that we sort of summarized in this table in a previous video. So here, we're starting with a ketone, and we're ending with an alkene. So kind of similar to the last one, we're starting with a ketone, we're ending with an alkene. So we could go along a similar path, do a reduction, and then an elimination. Okay, the difference here is going to be our choice of base in the elimination. But first, the rationale behind this, because you don't just want to memorize these paths. I mean, that's an important step, but it's really important to understand them because this will gradually become more complicated. And so it'll be easier to keep track of all this if you understand it. So the rationale behind this is we have an oxygen here, we don't have an oxygen in the product, so we need to get rid of it. We're going to do that one bond at a time. Right now there are 2 bonds between the oxygen and the carbon. Let's whittle it down to just 1. So we'd want to turn that into that alcohol. Now here we have 2 bonds to the electronegative element, here we have just 1. That, if the number of bonds to an electronegative element decrease, it's a reduction. So this is a reduction. Now we used lithium aluminum hydride in the last example for a reduction, and that would totally work. That would work here again too. Just for variety, I'm going to use sodium borohydride, so I'll show you how that would work. You'd have sodium borohydride, and the solvent is often methanol. And notice there are no numbers here. This is all in one pot. The numbers in front, the 1, 2 for the different steps, are crucially important. And with sodium borohydride, you don't have to do the 2 different steps. So it's often a faster reaction in that sense too, in that it's 2 different steps. Anyway, here we have this alcohol. Now we only have 1 bond to the oxygen. Let's knock it down to 0, whittle it down to 0 and get our product. So we're going to do an elimination. But like we saw a second ago, there are 2 types of elimination reactions. There's E1 and there's E2. You know you would have to do E1 if you had a tertiary alcohol. You know you'd do E2 if you had a primary alcohol. Here we have a secondary alcohol. The carbon that has the OH on it is bonded to 1, 2 other carbons. So really you could use either. Let's do the E2. So with E2, you would first need to turn the OH into a good leaving group. And you do that by adding tosyl chloride and pyridine. What you get after that step, instead of a hydrogen there, you'd have a tosyl group. So this is a good leaving group. That's what you would want to see when you see that OTS, good leaving group. And we drew the structure for that before. The reason why it's a good leaving group is because if it takes the electrons here and has a negative charge on this oxygen, this tosyl group has a lot of resonance in it, so it can spread that negative charge out through resonance and stabilize it. And if it's stable off of the molecule, then it can come off of the molecule. Once you have the good leaving group, you can do a base. Now this is where this exercise is more complicated than the last one. Look at the carbon that has the leaving group on it. That's the alpha carbon. Every carbon bonded to that is a beta carbon. We have a beta carbon to the right and a beta carbon to the left. So theoretically, we could do an elimination in either direction. We could do an elimination reaction to the right, in which case we would have this product, or we could do an elimination reaction to the left beta carbon, in which case we would have that alkene, the alkene form, the pi bond form toward the other beta carbon. Okay, so which one do we want? Well, really, we just want this one. Oh, oops, and when you form these, the tosylate group, the leaving group, leaves, of course. So we want the one on the left. We don't want the one on the right. So how do we choose? How do we get just the one on the left? Well, look at the two atoms, the two carbons in the pi bond. Then look at the number of carbon chains coming off of those. You have 1, 2, 3. So this is tri-substituted. Oops. So tri-substituted. If you look at the other one, look at the two atoms in the carbon chain, there's only one carbon branch coming off of that. That is mono-substituted. So what we want is the more substituted product. The more substituted product is the Zaitsev product, and the way that you get the Zaitsev product is with a skinny base. So you can either use sodium hydroxide, sodium methoxide, or sodium ethoxide. Just for variety, I'm going to use sodium methoxide. And what that looks like is you'd have the oxygen, the methyl group. Oxygen has a full negative charge, sodium has a full positive charge. So the Me there stands for a CH3. Okay, this other product is the Hoffman product. That's the one you'd get if you used potassium tertbutoxide. So once you have that Zaitsev product, oh, wait a second, that's it, we're done. And so that would be your answer. And so here, I'm just going to clear this out. If you used sodium methoxide, you get all the way up to your answer again. And this whole thing would be your final answer. That's what you'd want to include. So each reagent, then how that reagent changes the molecule, the next reagent, how that changes the molecule, the next reagent, how that changes the molecule. All of that would be required in an answer that would receive full credit. So here we've done some more multi-step synthesis exercises. In the next video, we're going to see about making new carbon-to-carbon bonds. So we'll finally start using those Grignard reagents.